Hello, it's Keith here, and this is lesson 12 of the Hello World series of my 650 assembly programming tutorials. Well, in fact, it's today the Hello Chibiko lesson. We're not going to create Hello World, usually I would, but today we're looking at the Atari 2600. And because of the quite serious limitations of the Atari 2600 hardware, I didn't really feel it was appropriate to create an example that showed Hello World. Now, compared to the other systems I've programmed in the past, the Atari 2600 is by far the lowest. Even the ZX81 had a character-based display where we could define characters on the screen. The Atari is far more basic. We're effectively building the screen one line at a time in software, and so we have to time everything and not plot the pixels as such, but define the pixels that will make up an entire line of the screen. So doing something like showing Hello World on a single line would actually be impossible. We could show the characters going down the screen, or we could show some of the characters on the line, but it didn't really feel that that was particularly constructive. Doing the kind of things I've done in the past where I show you how to show characters to the screen and use those character drawing routines to build up more complex routines wouldn't work on this system because we only have 128 bytes of RAM. We have no video RAM at all. We have no bitmap screen. We have no tile map. We have no tiles. We have no characters. So, as I say, it didn't make sense to me to try and do that. So what we're going to do instead is try and show a Chibiko. That's the mascot of the site. Should probably put the book advert up. There's the Chibiko advertising the book. So we're going to create this example on the screen here. The bitmap I exported with my AccuSprite editor in the correct format for today's example. And what I've done is I've created an example today that will build this image on the screen line by line, timing each line and setting the hardware registers accordingly to display the graphics to the screen. So that's what we're going to do. Now, first of all, before we do that, we need to discuss the sort of fundamentals of the actual hardware itself. Now, there's two things we need to bear in mind. As I say, firstly is screen timings, and then the second, for the display type we're going to use today, the actual hardware registers that control the graphics on the screen. The example today is being drawn with something referred to as the Playfield. Now, the Playfield is just a nice name for the background. Now, this is controlled by just 3 hardware registers, each of which take 1 byte. Now, these don't actually define the full width of the screen. They only define 1/2 of the screen, and there isn't a second set of registers for the second half of the screen. If you want to change the screen halfway across, you're going to actually have to change the registers while the screen is drawing and time it correctly. Now, these 3 registers define 1/2 of the screen, and then that half of the screen is mirrored onto the second half of the screen. Now, you can see I've set the 3 registers with various values here, so that you can see that the pattern is repeated on the left-hand side and the right-hand side. So this is one option, that is the normal mode. We can also mirror it so that the other half is a sort of mirror image, which you can see just here. So what I'm doing here is I'm tweaking various settings within my test code. You can download the test code. We'll look at it in a moment. But before we do that, we've got to discuss the actual concept of the hardware. So we've got these 3 registers. Now, 2 of these registers contain a full byte. The third register contains just 1/2 a byte. The high byte is used, the low byte is not used. Now, quite strangely as well, the middle one of these is actually reversed the bit order for the way it's displayed to the screen. The first register, PF0, actually uses only the high byte, and that's making up the first 4 bits of the screen on the left here. The second register is this middle part here, and that is the reversed one compared to the other 2, and then the third one is just here. And then they will be mirrored or repeated on the other side of the screen. Now, I've actually coloured the 2 sides of the screen here to make it clear. This is known as score mode. This is designed to show the scores at the top of the screen, and so it uses player 1's colour on the left and player 2's on the right. I think they're called player 0 and player 1, but it doesn't matter. Anyway, so that's that mode of colouring. The other mode is that there's a single colour for the foreground and a single colour for the background, but I'm using the scoring mode because it makes it very clear how that repeating is being done. And as I say, when it comes to our Chibiko example, what we're actually doing is we're actually very carefully timing the changing of the 3 registers so that basically this is register 0, PF0, PF1 and PF2 in this kind of area, and we're actually changing them after the first draw of those registers some point around here, so that by the time they're drawn a second time over here, they've actually been changed and the new data is in there for them. So it's quite a challenge, unfortunately. Now, it's not just changing the contents of the screen that we have to do in code and time correctly. We actually have to send the VSync signal and the VBlank signal for the actual CRT to refresh itself at the right times. And we have to time all of this correctly, so we need to understand the layout of the screen. We're using an NTSC screen today, and on that screen basically there is a couple of different things we need to sort of do. So there's the VSync, and that will last 3 lines. There's then VBlank, which lasts 37 lines. There's the 192 line screen, which is 160 pixels wide, I believe. And then there's an overscan area, which is 30 lines. Now, we don't actually need to do anything for overscan. We need to actually send the VSync and the VBlank signal, but overscan is just a thing that we have to wait for, basically. Now, the problem is, of course, is if we're drawing a complex screen like the one you saw here, we actually need to time each of those lines, and that's going to mean that our processor is going to be pretty damn busy doing just the job of the timing and changing any graphics on the screen. So we're not going to really be able to do much logic code there. If we had a simple game, we're going to have to put that somewhere else, and we can put that logic code in VBlank or in overscan. Those are the areas where we're not doing too much work, that we can actually do some thinking and not be always worrying about the next line. Now, when it comes to timing each of these lines, we basically have 3 options. Now, each line is 76 ticks of our CPU processor. So one option, the hardest option, will be to get the manual out and read the timing of each of the commands we use and time it that way. Very hard. Wouldn't really recommend that. So that's something I would suggest against. The most convenient option in most cases is to use the WSync. Now, all we do is we write any value to the address 02 in the 0 page. These are memory mapped hardware registers, and that is the WSync register, and any value written to that, doesn't matter what, will cause the processor to halt until the raster beam has got to the end of the line. And so when the processor continues, we'll be at the start of the next line. But there will be very little time until the screen starts drawing, so we need to be very careful there, and we might need to set things up at the end of the line for drawing at the start of the next line, because otherwise there might not be enough time to do them. So we do need to still be careful there. But WSync is a very easy way of waiting for a single line during this main screen drawing area. But it's not very convenient for VBlank and overscan, because we'll be using a lot of processing power just waiting for this WSync signal. So we want something more convenient there, and the best thing I think to do is to use the timers. There is a timer register we can set. There's various ones for various speeds, but the best one is the 64 tick one. So a value of 1 here will cause the timer to run for 64 ticks, which is just less than 1 line. Now, basically what we do is we set that timer, we do all of our program logic, and then we wait for the top bit of the instat register at address 285, and when that top bit becomes 1, our timer has expired. Now, there's a rounding issue because this timer is set in 64 tick multiples, so what we actually will want to do is we will want to use a WSync immediately after that timer expires, just as a rounding sort of correction, basically, to guarantee we are really tightly timed. I apologise for all that theory there. It's just necessary for a system of this complex. You know, there's no easy way of doing this. There's no firmware we can use to do the job. We've just got to do it ourselves. So that's what we've done. Now, how do we build our cartridge? Well, it's very straightforward. We need a set of vectors at memory address FFFC. The important one is reset, but we've also put a break register there, a break address there. So these are the addresses of the start of our code. Our code starts at F000 on a basic cartridge, so that's where we are here. We've got some options in our code here that we can turn on and off. 2-color is basically is the one that turns on the scoring color mode, which is where we can define 2 different colors for the left and right hand side of the screen. Half draw will disable the changing of the registers mid-line. It's just as a test, and you can see with this example it actually mirrors the left hand side twice, so not very practical for our Chibiko. And then the 3-byte is just another minimal example. Basically, this is just designed to show the test pattern for if you want to test the various registers and just see how the values are actually being represented. You can change these values here and they will just be replicated all down the screen. Very simple test for you to play with. So those are just some things that I've added in there. The main thing though is the drawing of the Chibiko mascot. Okay, well, the Chibiko mascot was created with my Aqua Sprite editor. You can see this is the bitmap I used for today's example. If you go to 6502, Atari 2600, this will export some ASM source code that is basically what I used to build today's example. And you can see that source code at the bottom here. Now, it's split into two parts, the left-hand side and the right-hand side. That just made it more convenient to work with. Each line, as it's drawn to the screen, is 4 bytes, the way I've done it. And so that is 3 bytes in native format for the Playfield registers and 1 byte for the color. Now, it's up to you if you don't want to use both, but this was convenient because it meant each line was multiplied by 4 to get the offset within this data. And I've split it into 2 for convenience. Now, one other thing that I found is I've had to put in a line statement here, a line 8. Now, if I disable this and run here, everything in the rainbow mode seems to work okay, and that's because we're only setting the color once per line. But if we enable 2 color mode, I think we'll find, yeah, there we go. You can see in this mode we've actually got some glitching at the bottom of the screen. Down here you can see that something's gone a little bit weird, and what's I believe has basically happened is the timing when we've gone over a 1 byte boundary has actually caused a very slight difference in the delay of the time the commands take to execute, and this has meant that one of the lines has taken slightly too long, and that's meant that the timing's gone out. So the line 8 there isn't because any of this data needs to be aligned, it's just to make the timing accurate enough for that very precise example where we're really we're kind of pushing things to the limit there with regards to the timing, and it's just gone out if we don't do that alignment. As I say, it's very particular how you time things, and it does make things quite hard to program on this system, unfortunately, but you can do it. So let's now go over some of the code that we're actually using. Now, first of all, let's take a look at this wait timer routine. Now, this is the delay routine that I'm using for VBlank and overscan. It's far more convenient than counting the lines in those cases. So all we're doing is we're reading in a byte from 285. That is the status of the timer. And so basically when the top bit of that goes to 1, then the timer has ended. And so if the value that's read in is positive, i.e. the top bit is 0, we're just going to keep waiting. When it becomes 1, we're doing a W-sync. We do that by storing any value to address 2. And that will basically wait for at the end of the next line. So that's effectively just a rounding, because as I say, the timer is 64 ticks, but the lines are actually 76. So our timer is not quite the correct resolution. So by doing this W-sync at the end, that will clear things up and make it perfect. Okay. Now, we've got this do game tasks routine. This is just run before the start of each new draw. It's resetting everything. So basically, we are storing the value 0 to our 3 Playfield registers, PF0, PF1 and PF2. These are the 3 at these addresses that define the 3 bytes that appear on the left and the right. Now, we're resetting them at the start because, as I say, as soon as we do a W-sync, the hardware is going to start drawing immediately, and we won't have time to load in any data from memory. So we're just blanking things out at the start of the screen, so there's no garbage shown before we intend it to. And for the same reason, we're setting the colors. We're setting player 0 and 1's colors with 6 and 7 for that 2 color mode, and we're setting the background and foreground with 8 and 9 here as well. And then we're finally setting Y and X. We use both of these. We use X as a scan line count for when we're drawing the screen. We use Y as an offset to our bitmap data. So we just need, again, to give that a default value before the start of the drawing of the line, because we're really racing that beam as it starts drawing. So we're just clearing everything down to some safe default values there. Okay. So at the start of our program, we're initializing the screen settings here. Register A in memory is the control for the playfield, so we can write a value of 0 for a normal playfield, 1 for a flipped playfield, 2 for the 2 color playfield, or 3 for 2 color flipped playfield, just depending on what we want there. You've got some test values there, so we'll just ignore those. This is our main frame loop. So the first thing we want to do is we want to start the VSync signal, and we do that by writing a bit 1, the value of 2 there, to the memory mapped hardware register at memory address 0, which is VSync. So that is starting the VSync signal. We then want to wait for 3 lines, so we do 3 W-syncs by writing any value to the address 2. We then ended the VSync by writing the value 0 to the VSync port at 0. That's turning the VSync off. Now what we want to do next is wait for the equivalent of 37 lines. Now this is just over 43 ticks of our timer. So we're writing the value 43 to our timer, and then we can now do as much as we want as long as we can complete it within that amount of time. So we're running our do game tasks routine here, and then we're running our wait timer, and so execution will continue at this point only once that time has expired, and then a WSync will occur. Now at that point we want to turn off VBlank, so we are writing a value of 0 to the VBlank port here. We turn VBlank on at the end of the last frame, so that's why we've not seen that yet. So what we're doing now is basically we're going to draw the lines, and so we've got to be super fast here. Now by the time we get to this point, the first line will have started actually drawing the PF0 register, because that's at the far left. So we're actually too late for that already, because we're so tight in timing here. So we're going to skip that on the first line. We will have a slight black area there maybe, but basically what we're going to do is we're going to do PF1, which is the middle around this position, then PF2, which is around here, and so that is doing the left hand side of the screen. Then what we're going to do is we're going to do PF0 on the right hand side, which is around here, so only 4 bits of that are used, remember, so we're doing that here. We're then doing PF1 again, which is this position here, and we're then at this point we're going to do the colors, and the reason for that is that PF2 might still be being drawn over here, so we can't change it for over here. So we're doing things a little bit out of order here. So what we're doing here is we're loading in our color data for the left and the right if we're in 2-color mode, and storing those to the player colors here. If we're doing the 1-color playfield, we are either loading in a color from the array here and storing that to 8, or we can use the X register, which is the line of the screen, for a rainbow effect. The alternative is we can actually use the values in our bitmap data for the foreground and the background. So you can see here, you can see we can use the red and the green from the defined colors within the table, bitmap table there. You can see though at the top there, our first line has got 2/3 of the way through before we've actually managed to start setting the registers, because of the various tasks that occurred up here, which is why I was blacking out everything before we were starting drawing anything, because I knew that things would be messed up on that first line because the timing is so tight. And then finally here we're setting PF2, so this is for the right hand side of the current frame. We're then calculating the Y offset for the next frame. We're taking the X position, the line number, and we're effectively clearing the bottom 2 bits, so effectively dividing it by 4, but then multiply it by 4 if you will, because we're using the same bitmap data for 4 consecutive lines, but each bitmap data entry is 4 bytes itself, so that we're basically getting that by clearing the bottom 2 bits here. We're then loading the PF0 value for the left hand side of the next line, which hasn't started yet, because as I say there'll be too little time after we do that WSync, so we're loading that and we're storing that in D0. This will be occurring around this position, so the playfield 0 is here and about here when it's repeated, so we're clear of that, so we can set it now. So that's why we're doing that here. We're then waiting for the WSync, which is waiting for the raster beam to get to the end of the line here, and then once we've done that, it will immediately start drawing the next line. And again, we don't really have time to do anything with regards to colors and things at that point. So what we're doing then is we're increasing our line count and checking if we're at the bottom of the screen, and if we're not, we're jumping back up here and doing the whole thing again. And as I say, we are so tight on time, we're using basically all the processing power drawing that image. Now if we were doing something simpler, maybe if we were just having a repeating image where the left hand side and the right hand side were duplicated or mirrored, we'd have a little bit of time here, but we'd want to use it for sprites and things, because the sprites are the same. If you want to have a sprite on the screen, you're going to again have to hand crank the bitmap data getting to that sprite, so it's very tough. It's very limited system. It's nothing like the systems that came after it, like as I say, even the ZX81, the ZX Spectrum. You might think those are basic systems, but nothing compared to this. So that's what it's like. Anyway, now at the bottom of the screen, we want to have a delay of 30 lines, which is 35 ticks of our timer here. So we are loading the value 35 into our timer here. We are then starting the VBlank by setting these bits here and writing that to the memory map register at address 1. We then run our wait timer. We've got no actual logic we need to do here, but you could do some if you wanted. And then we're just jumping back to the start to do frame, and we're just repeating forever. That's the entire program. So there's no there's no code that actually reads in our joystick or anything. We're going to do that another time. So there we go. That's all we've got for today. I forgot to tell you the name of the example. It's A26 Hello Chibiko. So feel free to go ahead and download that and have a go with it. And as I said, our Sprite Editor can help you out with regards to the bitmaps if you want to create your own bitmaps for the example. We're going to do a few more examples. So if you like what you've seen, please like and subscribe, because we'll be covering a few more things on the Atari 2600. I've got a joystick example, and we've got a sound example, and I've also got an example of how to use those sprites, which also uses the joystick. So if you liked this, please stick around, and please like and subscribe, because it encourages me to make more content. Hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.